All right, everyone. This video is the conceptual part of Chapter 6, Circular Motion and Motion of the Planets. Chapter 6, Circular Motion, Orbits, and Gravity. Gravity obviously is a pretty important force because um, we deal with it every day. It's what keeps us on the surface of the planet. And a big question in physics is what is gravity? What causes it? Is it caused by a particle or is it something else? A lot of people describe it as it's not really a force, it's actually caused by the curvature of space-time. Okay, so anything with mass causes space and time to actually bend, time also and space. And so that's what makes it seem like you're falling because space itself is actually being bent, and so you're falling into this sort of stretched membrane, almost like a quarter going around one of those circular things at the science center. Um, So gravity is really weird, and it's not really related to the other forces, at least that we can tell. So there are four fundamental forces. There's the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. And the other three are all related in some way, but gravity is sort of an outlier. We don't really understand how it's connected to the other forces. Some physicists would like to find a connection, but so far it's been pretty elusive. All right, but we're going to talk about the force of gravity. And the thing about gravity is it's different than the forces that we talk to because gravity acts over a distance, and you don't need anything touching in order for gravity to affect you. For example, the sun holds our holds our planet in an orbit. That means that our planet is attracted to the sun and there's nothing touching it. Okay, there's no physical connection, so it acts over a distance, and there's not anything that we can tell that's actually touching it. Okay, so a lot of forces act over a distance, and there doesn't need to be actually something bumping against each other, right? Like my fist pushes against my hand, and my hand pushes back, and they both exert equal and opposite forces on each other. Gravity's different. It works over a distance, really big distances. Actually, um, over something the size of our galaxy or even the universe, right? So gravity acts over very long distances, and um, two um, two galaxies, even though they're millions of light years apart, the closest galaxy, Andromeda, is 2.3 million light years away. And there's a gravitational interaction between our galaxy, the Milky Way, and our neighbor, Andromeda. So at some point, they're probably going to collide, but it won't be for some time in the future. All right. Well, let's get started here. I've posted a lot of these videos in the module for chapter 6. Uh, these videos are a lot of them are pretty good. There's some experiments that they do. I really like those ones because I don't always have all of the experiments here in my office. And so um, and anyways, the whole class is kind of on video. So these are some good videos. I'm gonna make as do as many of the experiments as I can. And if I can figure out a way to do an experiment, I will absolutely do it. I love doing experiments. Haha. All right. So definitely watch these videos. They're in the PowerPoint. You can get to them by clicking. I've posted a lot of them in module chapter 6. All right, but let's talk about circular motion, okay? We've been talking about motion in a straight line, but now we're going to start talking about things moving in a circle. So, for example, here we have these horse riders. They're going on a circular track, and if you're moving in a circle, there is something that is keeping you moving in that circle, okay? There's a force that keeps you traveling in a circle. Whatever it is, if you're driving, it's the force of friction. If you are on a planet like we are, then it's the force of gravity. It keeps you going in a circle. If you're on a merry-go-round, friction keeps you moving in a circle. Okay, we're going to talk a lot about circular motion and what that means. Um, but here's one example: horses going on a track. I used to do this to my son when he was much littler. I can't do it anymore now because he's taller than me, but you can swing your kid in a circle, and the dad is pulling on the kid's arms, and that's what keeps the kid moving in a circle. Okay? Okay. Here we go. All right. So how much force does it take a girl to swing the girl in a circle, right? It takes a certain amount of force in order to do that. And so the dad has to supply that force to keep her moving in a circle. We call that a centripetal force, okay? It's the thing that makes you move in a circle. There's this really awesome ride at the fair. It's called the Gravitron, and it spins really fast. And as you sit in the Gravitron, it basically goes so fast you lean against the wall, and then you kind of move up in the air. That centripetal force uh, forces these slides up, and so you're kind of stuck up against the wall. And you're like, and as you get older, you start to feel just incredibly sick. It's really horrible. Your body can't handle the centripetal force anymore. Okay, but you're still young, so you could go on the gravitron. This apparent force makes the riders feel heavy. You can feel that force pressing. It's like on your chest, like oh, you're stuck against the wall. Okay, that's the apparent force. Okay, so you're being pushed against the wall. The space station appears to float in space, but gravity is pulling it down actually quite a bit. Yes, things are weightless in space because they're constantly falling. It's just you're moving forward so fast that you miss the Earth. Okay, we're gonna talk about that. Okay, but gravity is still affecting the space station, but you're just moving so fast and you're falling that you feel weightless, okay? So you'll learn Newton's law of gravity and you'll see how the force of gravity keeps the station in orbit so it doesn't fly off into space. Right. And one important thing to remember is that anytime that your velocity changes, either the magnitude or the direction, okay, that means there's an acceleration because if velocity changes, that's only possible if there is some kind of acceleration. Okay, so let's draw a thing going in a circle. Okay, and maybe we can do a hammer throw. Okay, this is a sport in the Olympics. You basically got a long 1.2 meter chain here. There's a mass of 7.2 kilograms. Okay, and this thing is moving really fast in a circle. Okay, this is like tangent to where the thing is moving. It's going like this, right? It's going in a circle. It's going really fast. Okay. And basically, its instantaneous velocity this way is it's going 29 meters per second. Okay. So if I take, and this velocity is always tangent to the circle, that means that if I come up here, it only touches the circle in one point. Okay. So if I take this vector and I put it over here next to this one, okay, then it would look something like this. Okay, the direction changed. There's my vector. Okay, see the difference between this vector and this vector is that the direction has changed, and so there's a force here, and that force points towards the center. Okay, And this force, okay, that is our centripetal acceleration. Now I keep talking about a force, and so if you want to find the force, well, let's see, Newton's second law, F equals m times a. Force equals mass times acceleration. Okay. And so we can put this in here and we can say this is centripetal acceleration. Okay, we're gonna talk about what how to get centripetal acceleration. Okay, but I'm gonna throw it out here so it can be in the back of your mind. Centripetal acceleration. Okay, I'm just gonna throw up the formula here. Okay, and then we're gonna talk about it a lot. Centripetal acceleration is equal to v squared divided by r. Okay, v squared divided by r. Now this acceleration is a little bit different. Okay, because it's the magnitude of the velocity is not changing. Basically, it's your speed. Okay, your speed is not changing. So a good way to think about this. Okay, imagine you're driving in your car. Okay, so here's your car. You got a really cool car, maybe a 1969 Dodge Charger, like the Dukes of Hazzard. Okay, and you're driving in a circle. Okay, and you're on a big circular path here. Okay, maybe this is some or big racetrack, okay? Or you're just going in a circle here, totally driving in a circle. Okay, you're going this way. Okay, so now your speedometer, right? Your speedometer. Let's say you're going 80 miles an hour, so your velocity is 40 meters per second. Remember, 1 meter per second equals 2 miles per hour. I'm going to put a little squiggle here because that means about, right? About. It's actually 2.2 miles per hour. Okay, but if you're going 40 meters per second, you're in the 80 mile per hour range. That's the important thing here. Okay, so you're going 80 miles an hour, and your speedometer does not change. Okay, you got your foot on the gas, right? You're not changing your speed. What's changing is, so if I'm right here, right, my velocity vector is going this way, and as I turn, then my velocity vector is going this way. Okay. Um, and so the thing that's changing is not your speed. It's the speed is constant, right? That's the magnitude of your velocity. But what does change is the direction of your velocity. Okay. And that direction is basically creates there's must be a force directed towards the center. Right? There's something keeping this thing going in a circle. Okay. And whatever that thing is, that's the centripetal force. Okay. Your centripetal force. Yes, sir. Now, if for some reason, and that centripetal force were to go away, what my question to you is, what would happen to your motion? Okay, so let's say you're driving in a circle. Maybe, maybe you're driving down the freeway. Okay, imagine it's winter time. I know this because this actually happened to me. I'll tell you another story about the adventures of Dr. Neutron. Yes, back when I was a young Dr. Neutron, a lot less wrinkles. You see, I've been too close to a large object with a lot of mass, and gravity has caused me to move through time, and so a little bit more wrinkly, a little less hair here and here. Anyways, I was a much younger Dr. Neutron, and I was driving, and it was pretty snowy. It was pretty snowy, and I was going around a corner, and I was 18 years old. And I had just gotten a new car, okay, and it cost about $300. Now, this, of course, this was in the 1990s, okay? But let's just say that even in the 1990s, $300 was not a lot of money to pay for a car. I was missing a few side panels. The tires had no traction. It was totally smooth. It did run. You could drive. It didn't it you know it had seat belts, but that was about all the things that it had. Had windows. The side panels, a lot of them were missing. So anyways, I got this car for $300. I was driving it to school, and it was snowy. And I remember I had a test that day. And I had been late a few times to class through no fault of my own, of course. But I was going around this corner and it was snowy and I was gonna be on time that day. But okay, what happened was my centripetal my centripetal force disappeared. My tires started going in the from static friction, which is much higher, by the way, because I don't know if we talked about that a lot, to kinetic friction. That means basically my car started to slide. I went around a corner, and what happens? Well, when you start to slide, you continue forward at whatever trajectory you were on when you started to slide. So let me show it. So let's say here, this is Dr. Neutron and he starts to slip around the corner. Okay, the road continues this way. Okay, but what happened to Dr. Neutron is he went this way, and my car was spinning around. Yes, a little circular motion there on my car. See, there's the circular motion from going in a track here, but then there's also the circular motion from your car spinning. Okay, so but the center of my mass was continuing this way. And that's exactly what happened because as soon as you start to slip, okay, you immediately start moving in a straight line. All right, let's talk about merry-go-rounds. I don't know when the last time was that you were on a merry-go-round, okay? But now you probably remember from maybe when you were a kid, okay? But I've been on a lot of merry-go-rounds the past few years because I had a kid, and so you have to ride with a kid. Now, thinking about a merry-go-round, as it's spinning, you feel a force which seems like it's pushing you outwards, okay? And so you've got to hold on to counteract that. But what's really going on is that you just want to continue forward, okay? That's the key. When you're going in a circle, right? You're turning like this, okay? Well, you want to basically continue forward. So, um, it's not that you're spinning outwards away from the center. It's just that you want to keep going forward, but the merry-go-round makes you turn, okay? Now, if there's no friction on the merry-go-round, you'll just keep going in a straight line. True story. Okay, let's now I do have a wait, but it's know if I'm gonna destroy something. What can we do? Oh, I know. We're gonna launch Pikachu. Ha ha! Pikachu! I choose you! I choose you, Pikachu! Oh, okay, we're gonna make a harness for Pikachu. Yes. Hmm. Gotta move away. Move away from the camera. Okay, here we go. See, here we go. Pikachu's going in a circle. And let's see, no, not, not helping Pikachu. Well, that didn't work. Okay, you can't really see anything. Let me turn off this too. I, I don't want this. Oh, yes. I don't know. The AI decides where the camera looks, which sometimes is good, but other times it's the opposite of good, which is ungood. Okay, so Pikachu. Here we go. Let's. One for you. But see that he sort of continued straight. All right, well, you know what? This would be a great time to build your own contraption. Yes, and this actually, yes, this brings me to one of my favorite sections, the medieval weapons section. Okay, so now I'm gonna make a video tomorrow and I'm gonna show you how this works. I'm gonna go outside. I can't do it in this video, so it's gonna have to be a separate video. But basically, what I've done here is I've taken this 3 pound weight, about 1.2 kilograms. Okay, now maybe that doesn't seem like a lot, but it's attached to this meter long rope. Okay, now, um, let me tell you, if you get this thing spinning around, I can make it fly through walls, boards. I was actually doing this last semester and I was launching it up in this classroom. I'm going to try and find a video of that. That was really amazing. I'm going to go outside and do this tomorrow and I'll post a video of it. But this is my weapon, okay? And if you spin it in a circle really fast, man, you can do some serious damage. All right. This motion is entitled Circular Motion, Orbits, and Gravity. Okay. And hopefully you watch. There's another video which talks about some of the key equations, and I posted a lot of these videos in Canvas, so please watch those. Okay. Um, Anything that is moving in a circle is accelerating, right? And we know this because the only way that things can move in a circle is if there's a force constantly acting on that object. Things don't just go in a circle without a force acting on it. We know that from Newton's law because an object that is in motion will continue in motion in a straight line unless acted on by an outside force. So Newton's first law. Um, if it has a velocity, it's going to go in a straight line, unless there's a force that changes the velocity. So in this chapter, we will have a changing velocity, but the magnitude of the velocity is not going to change. Only the direction of the velocity will change. So um, let me draw a quick diagram, right? And we'll see later also that we can apply the same kinematic equations to circular motion with some slight modifications. Okay, so we can actually use these to treat objects moving in a circle, but we'll get to that in a little bit later. All right, so let's say we have some object, and we could have maybe Pikachu. Okay, so Pikachu moves like this, and then his velocity starts to change, and he goes in a circle like this in some way. Okay, so uh, Pikachu's path curved like this. Okay, well, here's my velocity vector. Now, I tried to draw these so that the magnitude of the velocity vector doesn't change, meaning the length is the same. But if I move this velocity vector up here, right, the length is the same. The only difference is the direction of my velocity has changed. Okay. So the direction has changed, and that change in velocity, remember, um, we have A is equal to delta V over T. That is acceleration. Okay. And so the change here occurred like this. Okay, that green arrow points towards the center, right? It points towards the center, and so um, that is going to be the force that pulls it towards the center. Okay, and I'll just throw this out here right now. Okay, but we can write down the formula for centripetal acceleration as v squared over r. Okay, that is going to give us the formula for centripetal acceleration. That's how much that this force is equal to right there. And so every time, right, if I get in here and I draw this, right, every time if I move this velocity vector up here, okay, again, we also have another change in velocity right there, okay, also pointing towards the center. So write this down on your card, a very important formula, v squared over r, okay? And we're just talking about a change in the direction of our velocity anymore, okay? Gravitron. When I used to go to the fair when I was much younger. There was this ride. They probably still have it. It was called the Gravitron, and you get on this cart and you lean against the wall, and the walls are kind of tilted like this, and then it starts to spin. It's like, and I am sure if I did it now, I would completely vomit. And the centripetal force, right? You want to continue forward, but the wall pulls you in like this. And so and then you start to slide up the walls because it's kind of at an angle. And so it pushes you up the wall. And imagine if you vomited instead of the vomit going straight out of your mouth, it would continue in a straight line, and so just cover your cover your whole face. Oh, I can't imagine vomiting on one of those. It would be truly horrible. The International Space Station, it appears to float, but it's not actually floating. Gravity is still acting on it very strongly. It's just that the space station is moving so fast this way that when it falls, it misses the Earth, right? That's how you put something in orbit. It's like it's going this way and it's falling. But it's so fast that it misses the Earth. It's constantly missing the Earth. And so that's why that you experience weightlessness is because you're constantly falling. Okay. Some people can't handle weightlessness. There's this plane called the Vomit Comet where they train you to be an astronaut. They go up really high and then they drop. And you for a few seconds you have this sensation of weightlessness, and a lot of people vomit. I remember I went to Dollywood. This is probably the closest thing I've done to experience a free fall, but there's a ride where you go up. I think it's 300 or 400 meters, maybe about 200 meters. Well, I don't know that actually that tall, but it's pretty high. And you get up there and you're in this chair, and then you just drop and you fall for about, I don't know, maybe 100 meters or something, but it is really scary and it's a truly horrifying sensation. I don't like free fall, but I'm glad I experienced it because I want to know, I want to feel the physics. Oh yeah. Go to Dollywood, and they have that other places too. All right. So we learned that an object moving in a circle at constant speed experiences acceleration directed toward the center. Okay. And then in this chapter, we're going to learn how to extend Newton's second law, which relates acceleration to the forces that causes it. Okay. To this type of acceleration. Okay. So I'm going to give you a spoiler right now because, you know. Life is short, okay, and I'm just gonna throw this equation out here, and then as we go through the chapter, okay, we can talk about what it means, okay? So, all right. So if this is an acceleration, okay, Newton's second law is still true, okay? If you don't remember anything from this class, okay, F equals ma. Just this one equation. Please remember this one equation. Okay, because guess what? It doesn't matter. It doesn't matter. And that was a famous guy said that with the same haircut as me. It doesn't matter. Okay, it doesn't matter what kind of acceleration you put in there. Okay, so if guess what? If you have F equals ma, you can have centripetal acceleration. Okay, you can put in v squared over r. Boom. Okay. Now we have the centripetal force, right? We have the magnitude of the centripetal force, and it's in newtons. Yeah, newtons, baby. There it is. Yes, I'm gonna draw these square brackets. In math, it means that's the units of force. Okay. These are the big equations that we're gonna use in this chapter. Okay, there's a couple of them. Anyways, so what do we have here? Well, we have the magnitude of the centripetal force, okay, and we have centripetal acceleration. So I'm gonna put a C there for centripetal force. Centripetal force. Nope. There's centripetal force. And there is centripetal acceleration. All right. Centripetal force. A equals V squared over R. Centripetal, that's some centripetal acceleration. A equals V squared over R. Centripetal force. M times A or M times V squared over R. Boom. Pen drop. Um, anyways, let's move on. We gotta get through this quick so we can do some problems because man, my videos are too long, talking too much. I mean, what else am I supposed to do in a video? Okay. A softball pitcher is throwing a pitch at the instant shown. The ball is moving in a circular arc at a steady speed. Yes, it is. Okay, I'm gonna put my. Here we go. Okay. Uh, at this instant, the acceleration is what? Okay. So she is doing an underhand pitch. They're amazing. They can get the softball going like 70 or 80 miles an hour. Crazy, underhanded, okay? And so, what direction is the acceleration directed? Is it up, down, left, or right? Well, one thing you need to remember, okay? Centripetal acceleration always points to the center. And so, if the ball is to the left of her, the center is her shoulder, and so I'm gonna say the right. Yes, because that's the center of the problem. All right. Reading questions. Hopefully you read the chapter. You should read the chapters. I mean, they're pretty good, although we do have a limited amount of time. So read them as much as you can. Look at the PowerPoints, and hopefully these videos help you too. Uniform circular motion, the acceleration is parallel to the velocity. Well, usually the velocity is tangent to the circle. Okay. Let's draw a picture of that. There's a picture. Okay. Okay. Let me back up here. All right. So usually, let's take the example of the softball pitch. Okay, so she is bringing the softball around here. Okay. And the velocity is tangent to the circle, so it's pointing this way, right? It's tangent means it's touching the circle basically at one point. So I take a straight line here and I put it next to the circle, and it's only supposed to touch the circle at one point. So over here, the velocity is directed this way, and then over here it is this way. And I forgot what the question was. Uniform motion, the acceleration. Oh yeah, which direction is it? Well, remember we always said that no matter what, the acceleration should always point towards the center. Okay, um, unless it's speeding up, but it's not. It's at a constant velocity. So, the answer is pointed towards the center. So parallel to the velocity. Nope. It's directed toward the center of the circle. Yes, it's B. Is larger for an orbit at the same speed? I don't know what that means. No. Is always due to gravity? Nope. Because usually you're swinging it around. Is always negative? Nope. It's B towards the center of the circle. All right. Want to Car turns a corner on a level road. Which force provides the necessary centripetal acceleration? Yeah, there is friction, I would say. I mean, gravity keeps you on the road. There's no tension. At least I don't know where that would be from. Air resistance or is air resistance always, but that doesn't keep you going in a circle, and that's definitely not it. Normal force is the force between you and the ground, which is important to friction, but no, the answer is friction. Friction is what keeps you on the road. If you lose, oh wait, you can't see my screen. You can't see my screen. Bro. All right. So, uh, question is, when a car turns a corner on a level road, okay, which force provides the necessary centripetal acceleration? It's friction. That's the only force acting on you that can keep you on the road. Okay, so the answer is friction. All right, moving on. A passenger on a carnival ride rides in a car that spins in a horizontal circle as shown at the right. At the instant shown, which arrow gives the direction of the net force on one of the riders? Okay, think about that for a minute. I'll give you a second. Okay, they're going in a circle. This is on a Ferris wheel. No, it's some random carnival ride. Hopefully, it's not that octopus one, where you're spinning in a circle, and then there's like three arms attached to that one, and then those also spin in a circle because that is horrible. And actually vomit, but that's the closest I've ever been to vomiting on a ride, right? Because you've got these big things going in a circle, right? A bunch of arms, and then attached to the end of those, okay, there are three little arms that have the carts in it. And so if you're unlucky and you get with some jackass who's like, "I'm gonna spin this cart," and then you're spinning your cart spinning, and that's going around in a circle, it's like, oh my, that's worst ride ever. Okay. Anyways, all right. Hopefully, you had time to think about it. At this position, D points towards the center, and so it is D. Okay, because that's the only one. Centripetal force always points towards the center of the circle. All right. How many times per day does the International Space Station or any satellite in similar low orbit go around the Earth? Um, well, the space station has to be going really fast because remember I said like basically here's the space station, right? It's I throw it, okay, and okay, so as I'm throwing it, right, I throw it like up here, okay, it starts to fall, okay, but it's going so fast. Here's the Earth, the end of my finger there, okay, it goes so fast it falls and it misses the Earth. So see, you're constantly falling towards the Earth, but you're going so fast this way that you miss. Okay, so it's got to be going really, really fast. I think it's so fast, it's more than five. It's got to be 15, but yeah, I don't know how you know that. You should have read the chapter. That's how you know it, because you read the chapter, but very fast. Space station is going very fast. Newton's law of gravity describes the gravitational force between the Earth and the Moon, the Earth and the Sun and the planets, a person on the Earth, or all of the above. Yes, gravity is the universal force that it connects us all. Every atom in the universe has a gravitational pull on every other atom in the universe. Maybe that's what Luke Skywalker was talking about, the force that connects us all. Was it gravity? I don't know. But yes, gravity works on everything, all of the above. All right, section uniform circular motion. All right, we made it through the conceptual parts. All right. Here's that equation. A equals V squared over R. Okay. Very important. This equation, we'll use it a lot. Okay. Notice that the velocity vector is always in the direction of motion of the thing going in a circle. Okay. And it's tangent to the circle. The centripetal acceleration is perpendicular to that, and it always points towards the center of the circle. Okay, so this is a very, very important equation. Centripetal acceleration for uniform circular motion. Okay, it's a little bit different if the thing orbiting is speeding up, but more all the systems that we're going to deal with, the magnitude of the velocity is not changing, and that's uniform circular motion. Okay, a ball at the end of a string is being swung on a horizontal circle. The ball is accelerating because the speed is changing. What did I just say? No. The magnitude of the velocity doesn't change. The direction is changing. It is changing indeed. If I have my yes, this is my medieval weapon. Okay, this thing's actually pretty lethal. Okay, if I spin it in a circle, it's like 3 pounds. I want to destroy my computer. Okay, but as it's going in a circle here, its velocity is changing directions. Okay, but the speed is not. So you should make something like this. Okay, go get a rope somehow and get something that weighs about 3 kilograms, and I'll make a video, and we're gonna make a weapon. Yes, some kind of medieval. It'd be like kind of the hammer throw in the Olympics. So this is actually a sport, except this mass is 7 kilograms. This is only 1 kilogram. 7 kilograms is a lot. All right. So the speed and the direction are changing. Nope. Only the speed. Nope. Only the direction. The ball is not accelerating. Well, if it's going in a circle, it is accelerating, so it's only the direction is changing. Okay. A car is turning right at a corner on a constant speed. Top view of the motion shows in the figure below. The velocity vector of the car points to the east at the instant as shown. What is the direction of the acceleration? Well, if it's going in a circle, it points towards the center. Okay, and on according to my compass over here, and where's the magic marker? Yes. My vanishing marker. This is my compass. Okay, it's right there. So the center of the circle is south. Okay, then the acceleration is pointing to the south. Here is the center of the curve. Okay, it always points towards the center of the curve. We're really trying to emphasize that a lot. Okay, the curve that the car is following is a segment of a circle. Okay, yeah, it's uniform circular motion for uniform. The acceleration is described toward the center of the circle, which is south. Okay. The ball at the end of the string is being swung in a horizontal circle. What is the direction of acceleration of the ball? Tangent to the circle in the direction of the ball's motion or towards the center of the circle. It's always towards the center. That's it. It doesn't point any other way. Okay? It points towards the center. Why do they keep asking me this? I'm not really mad. It does always point towards the center. So I don't know in this PowerPoint they ask it like a lot. Just always say the acceleration if it's going in a circle, it points towards the center. That's it, man. It doesn't point any other way. All right. To prove it, we're going to do an experiment. Yes, time. Time for an experiment. I think it is. Yes. All right. We're going to get out force meter. We're going to prove once and for all which way. Oh, this is the thing I have to plug into my computer to get the force sensor to work. Which way is the force sensor? Is the force of the circle? Okay. Here it is. Okay. It's this thing. All right. So on the end here, there's a force sensor in here, and it's going to transmit that to my computer. I'm going to put it on the screen. Okay. So we gotta go to the website. Oh, um,
Thank you, like and subscribe down below.